Hello everyone. In this lab project, we are going to make and simulate the half subtractor and full subtractor. So before we start to make that, let's take a look to the half subtractor and full subtractor and see what they means. So let's start with the half subtractor. The half subtractor is very similar to the half adder. So if you remember, in a half adder, you have actually 2 bits as an input and two bits as an output. It's add the inputs and they give the result in the output. So the half subtractor is almost close. So if you have one unit, we call that half subtractor. It's able to give 2 inputs, which is A and B. And whatever you have in the output is actually A minus B. So that means if I call these Z, so the result should be A minus B. So if you are doing A minus B, if, for example, A is 0, the B is 1, definitely you get negative numbers. So that's the reason you have 2 outputs. So one usually shows the sign and another one I call the C, which shows the real value that you have. So if we make a functional table for that and see what could be the old and list all possible cases that could be happen in this circuit. So you say, okay, you have 2 inputs A and B, each one could be 0 and 1, the 4 different bit pattern or situation you could have in the input. So you have 2 output. We call one as a sign, which shows the sign of the subtraction, and one C, which shows the absolute value of that. So for sign, you could have here, you could say if the sign is a 1, it means the number is negative. The result is negative. If that's 0, it means positive. Okay. So let's start and check if each condition. So whenever you have both 0 input, 0 minus 0 is 0. And you could consider 0 as a positive number. So you say, okay, 0. Also, it doesn't matter whenever you have 0. If even this is 1, it doesn't matter because the 0, it's not positive, it's not negative. Whenever you have the 0, you never take a look to here. So, but based off the circuit that we have inside this, that circuit make the 0 whenever you have both 0. So how about 0, 1? So you have 0 as a 1 as a B. So 0 minus 1 is 1, but the result is negative, that you have 1. So how about next? This is 1, this is 0. 1 minus 0, you have 1, positive 1. For that reason, sign is 0. This is 1. And whenever you have both 1, 1 and minus 1 is 0. Again, it doesn't matter. You could put actually the X, which is if it's 0 or 1, it doesn't matter because whenever you have 0, the sign is not matter. So definitely 0 is not positive and negative. But based off the circuit that we have inside that circuit actually make us a 0. Okay. So this is how the half subtractor should be worked. Definitely you have inside this, you have the gates, which do the same task. So if you didn't watch the half subtractor video in a digital playlist, please watch that video, and I explain in that video how you could design the half subtractor. So similar to this, we have one unit which we call that full subtractor. So what is the full subtractor? Similar with the full adder, it is a unit. So we call that full subtractor. This time, unlike the half adder, it has 3 inputs. So which is A, B, and C, and give you a 2 output, because if you subtract, you never have more than actually 1 bit. So that's the reason we say you have 1 output. I call that C, which is the real number that you have. And similar with the half adder, another one should be keep you the sign. So what is the output? Output is doing this A minus B and give you A minus B and minus C. Usually based off its design, usually it's do first A minus B, whatever you got, and it will be subtract from C, because in the lecture I explained you could use actually the half adder and you are able to make the full adder. So same thing here, you could use the half subtractor to make full subtractor. So please watch the full adder and the half adder and also subtractor videos if you didn't that. So let's do similar with the half adder. Let's do just check the all possible cases that you could have. So you have A, B, and C. So you will have the 8 different bit pattern in the input you could have. So let I just list all of them and see what it should be the output for each of them. So let's just complete these 8 cases. So maybe it's better to separate these each different input that you could have. So then we will have here as an output 1 for sine, 1 for C. So complete this table. So let's just complete the left side. So 2 0 2 1 2 0 2 1 and 0 1 0 1 0 1 and 0 1. So that means here on the left side I list the whole possible bit pattern that you could have as an input, which is you have 3 bits, each one could be 0 and 1, so that means you will have 8 different bit pattern in the input. So we start with the first. Whenever you have 3 0, so you have A minus B minus C. You say 0 minus 0 minus 0, so the result is 0. So you put 0. So again, it doesn't matter what you have here as a sign. So I put here X, which is the don't care. So we don't care it is positive or negative. But based off the circuit, it will give you a 0. So the next is 0 minus 0 minus 1, which is definitely should be negative 1. So you should have negative again. 1 is negative and the 0 is positive for the sign. Okay. So 0 minus 0 minus 1 should be negative 1. So that's you have this is 1 and this cell that's negative. So the next is 0 1 0. So for this you have 0 minus 1 minus 0. Again it is a negative 1, you have 1 1. So the next is 0 minus 1 minus 1. So this one is you say 0 minus 1 definitely is 1, and you subtract 1 minus 1, you will have 0, right? Or you could say 1 minus 1 is 0. So again, you have the 0. We don't care what we should have in this sign. So, but the circuit that we have, and I show in simulation, is give you a 1. But whenever you have the 0, it doesn't matter the sign, okay? So how about next? 1 minus 0 is 1. 1 minus 0, again, you have 1. So definitely should be give you a 0, 1. And the next you have 1 minus 0, which is 1. And again, minus another 1, which is this. You will have the 0. So again, I put here 0. I put here don't care, because whenever you have the 0, you don't care. It is 0 or 1. The sign. So the next is 1 minus 1, again 0. I don't care about this the sign. It could be anything 0 or 1, but this C should be 0. And finally, whenever you say y minus 1 is 0, and 0 minus 1 should be negative 1. So that's the reason you have 2 1 here. So we are going to simulate the both of them, the full adder and also full subtractor, and also half subtractor with the multisim. So if I stop this and go to the half subtractor, so start to simulate that. This is its simulation. So let I just zoom that a little bit, which able to see in okay. So let's see if I could do more. And maybe more. Okay, right now it's better. So as you could see here, this is actually your black box that I labeled as a half adder. You have 2 input. You could give 0 1, and this is your 2 outputs. This is your signature sign. This is your sign, and this is your numbers. Okay, so start with 0 0. Okay, so if I put 0 0, the result is 0. I don't care about the sign, and the circuit gives 0, but also I don't care because that's a 0. So similar things, if I give both 1, so 1 minus 1 is 0. So again, I don't care about the sign, but also it's give the 0, which tells somehow is positive. So see the next. This is your A, this is your B. This circuit give A minus B. So if I give 1 minus 0, so it should be 1. This is 1 because connected to the VC. 1 minus 0 should be 1, and the signature should be positive, which is 0. So C positive 1, it is right. So if I put this 0 and put this 1, so you have a 0 minus 1. 0 minus 1 is negative 1. So see, this is telling you negative, and this is 1. So as you could see, it's actually works. So if you could actually verify the all 4 different conditions that you have, and definitely it's work based on what I explain here. So which is, we test most of them, okay? So again, you could test that 0, 0 again is 0, 1 minus 0 is 1, positive 1. And again, you could say 0 minus 1 is negative 1, and again 0 minus 0 is 0. So it works. So, and let's check the subtraction, full subtraction. So again, let I zoom this a little bit. So just a little more, yeah. So see, whatever you see here, so whatever you see here, this is actually the box that I show with the black box, okay? So I already explained in the lecture how you could design the full adder, and this is inside that box. So we already know that, so we considered this as just a black box. You have 1, 2, 3 inputs, and you have two outputs. So this is the sign, and this is the number. So let I back to the half adder, stop the simulation, and back to the full subtraction. So let's do just, simulate this and see what we get. So as you could see right now, I already simulate that. So these are my 1, 2, 3 inputs and 2 output. This is the sign, and this is the number. So see, let's try start with the 3, 0. So definitely based off the table that I show you. So whenever you have 3, the sign should be, it doesn't matter. So here it gives you 0. So, and this should be 0. So you have 0, so which is works. If I just put a 1, so see, this is 1 minus 0 minus 0. So definitely it should be 1. So see, positive 1. This is 1, this is positive 1, okay? So you could test all of them. So let's do just start from the first line of the table, and let's do this. Let's do just verify the all part of this table that I mentioned here. Let I just put the all of them and see if it works based off this table that we expect. So I put actually 3, 0. So you have 0, it works. So then I put actually C, which is the last one, as a 1. So that means you have 0 minus 0 and minus 1, which is negative 1, right? So this is negative, this is 1, it works. So the next is based off the table. The middle one, B, is 1. So these two is 0. So that means you have, again, 0 minus 1, which is the negative, right? So that's the reason negative 1, you see negative 1. This is the sign, this is the number, it works. Go to the next A is 0, the both B and C is 1, so which you give you the 0. So this is 0, it doesn't matter what you have. I put as a don't care in the table, but here you see based off this circuit, it give you a 1. Again, because this is a 0, it doesn't matter. This is don't care. If it's 0 or 1, we don't care because we know the result is 0. So the next is you change this 1 and these 2 is 0. So again, you have 1. 1 minus 0, 0 is 1, and this is positive 1 because the sign is a 0. So if you change that to the 0, put these 2 is 1, that means you have 1, 0, 1. Again, result is 0 and 0, that's right. So if you put A and B as a 1 and C as a 0, again, you have the 0. Also, we don't care about this sign because the result is 0, okay? But circuit give 0 in this case. So, and finally, you put all of them 1, definitely you get negative 1. 1 minus 1 is 0, 0 minus 1 is negative 1. So you see is negative 1. So as you could see, your circuit actually works and you simulate and made one full subtractor. So let's go to the breadboard and use the TTL circuit, TTL IC, and make the same circuit with the gates and check that with the TTL circuits. So here I have the both circuit which implement with the IC. So here I have the half subtractor and here we have full subtractor. So let's test the both and see they works or not. The circuit is we implement exactly the same circuit that you saw in the simulation. So let's start with this half subtractor. So we implement the same circuit that you saw in the simulation. Here these two switch in the beginning is one is this is A, this is B, and here this LED is the sign and this is your bits. So I'm going to test all possible inputs that you could make. So I start for both 0, A is 0, B is 0, 0 minus 0 is 0, the sign is off and the character or the C bits is off. So that means 0 minus 0 is 0, 0, which is right. So now I'm going to check the next. So I keep the A0, B1. So A0, B1, 0 minus 1 is negative 1. This is your negative, this is your 1. So it is right. So the next you have A is 1, B is 0. So that means 1 minus 0 should be 1. And the sign is 0, which means positive, which is right. So now I put both 1. You have 1, 1. So 1 minus 1 is 0. The both is off. So as you could see, we implement that and it's worked exactly same in the same way with the simulation file that we have. So let's check the full subtractor, which is same circuit that you saw in simulation. So here, this is our three inputs, these three switch. This is A, this is B, this is C. I put them back. So see, this one is A, this one is B, this one is C for the full adder, A, B, C. And the LEDs, so whatever you have here is actually your lowest value bit, and this one is your sign. So let's again check the all possible inputs that you could make and see it's actually subtract the 3 bits or not. So right now A is 0, B is 0, C is 0. So 0 minus 0 minus 0 is everything is 0. So the output should be 0, 0, which is right. So next I'm checking 0, A0, B0, and C is 1. So 0 minus 0 minus 1 is negative 1. This is negative, this is 1. It works. So the next I check 0, I check 0, 1, 0. So that means A is 0, B is 1, and C again is 0. So A is 0, B is 1. 0 minus 1 is negative 1, minus 0 again is negative 1. This is negative 1, so it works. So next I'm checking 0, 2, 1. So that means A is 0 and A is 0 and B and C is 1. So A is 0, B and C is 1. So that means 0 minus 1 minus 1. So 1 minus 1 is 0. So you should have 0. So you see this lowest value bit is 0. And sign is 1, which it doesn't matter, right? So whenever the result is 0, no matter you have 0 or 1 for sign because 0 doesn't have any sign. So this circuit that we use in this case give the sign 1, which somehow is don't care, right? So because whenever the value is 0, the result is 0, no matter what you have in the sign. But this circuit give 1, which is, it doesn't matter. So it could be don't care, so it should be fine. So go and check the next. We check actually 0, 1, 1. So next should be 1, 0, 0. So that means the A should be 1 and these two should be 0. A1, B0, C0. So that means you have 1 minus 0, which is 1. So 1 is on. And the sign is 0 means you have positive 1, which is right. So let's check next. Next, you could have 1, 0, 1, 1, 0, 1. So that means the A should be 1. So this should be 0. And the next one should be 1, 1, 0, 1. So again, 1, 0, 1, 1 minus 0 minus 1. Again, you should have 0. So you have both 0, which is fine. So the next, you should have 1, 1, 0. So that means A is 1. B is 1 and C is 0. So C you have actually 1, 1 for A, and B is 0, and this one which is C is 1. So that means 0 minus 0, 0 minus 1, you have negative 1. So the negative 1 is right. So we check actually we check one to see what we checked here. We checked so we checked 0, 0 minus. We actually already did this. So what we need to check is 1, 1, 0. So I actually did that mistake. So this is A. So that means it should be 1, 1, and this one should be 0. So the last one we checked is 1, 0, 1. So for this time we need to check 1, 1, 0. So 1, 1, 0. So A is 1, B is 1, and this is 0. So 1 minus 1 is 0. You got the both 0 is right. And the last one we need to check is all three is 1. So that means A1, B1, and also C1. I actually changed the C to 1, A1, B1, and C all is 1. So 1 minus 1 is 0. 0 minus 1 is negative 1. So that's the reason you see negative and the 1. So as you could see here, we actually checked all possible bit pattern that you could give from two inputs, and for all of that scenarios, we checked the output, which is you saw this circuit works as a full subtractor, which able to subtract 3 bits. So I hope you like this video. Thank you for watching.